Yeah, I was not motivated during undergraduate, and I'm telling you, I've been a mediocre for many years. But I started performing in graduate school because I found out, I start getting really good advice, and I found out like following this track can give me a really good job in the U.S. So that's why I got motivated, start working hard. Um, I was not able to get the advice I'm giving you guys when I was in the college. So I think um, you guys have this kind of experience from me. Um, please prepare for that, for a job. Think about that earlier. All right, so we have been doing this kind of problem for a long time. The reason that this 5 volts is contributing 2.5, not 5, right, to VL is because if you're doing superposition, you are going to short this voltage source. So all these are grounded. And if you are looking at this one, this is actually 2 resistors in parallel. It's giving you 1K. And then 1K being added to this 1K, you're getting 2K. And because this is shorted, so 2K, 2K is still 1K. And then 1K here is 2K. So it's 2K, 2K is the voltage divider. So 5 volts is going to contribute 2.5 to here. And this one will contribute 5 over 4. And this is 5 over 8, which is 1 LSB. Okay. Yes, you have to show the process of the calculation, but after you are done with that, can you just verify it really quick? Before submit it, right? I'll verify this really quick. It's 1.25 plus 2.5. So that's the final result. So you have failed this problem in the quizzes, in the homework assignments. I don't think you should fail here in the midterm. You have been doing this for that long time, for like at least 3 times. And if you just directly do this, only took me like 5 seconds. If you just write this down, I won't give you 0 points. I'm going to give you some partial credit. You're probably getting more credits compared to whatever you have done on the paper, right? But you have to show the process. I can tell you, you really don't look at it. It takes so long. I just look at this number. No, but I still give you partial credit if you show the process. They can tell you know what you are doing, right? So that's how I can make a conclusion. Think about it. You have failed the first time, and the second time you make a conclusion from this. That's how it is differentiate you from other people, from mediocres, right? Because you can get full credit from this, but other people cannot. What's the conclusion? This one is contributing 2.5. This one is contributing a quarter of the overall voltage. And this is contributing 1/8 of the overall voltage, right? That's a conclusion, and remember it. So it won't fail next time. What's this one? One thing you want to remember is the DAC feeds back the signal to the inverting terminal. So which means whenever this voltage, 6.2 volts, is being held over here during the conversion, whenever this is higher, it's reporting a 1 to it. So you have to remember that because I didn't draw that diagram over here. So you have to know that DAC is feeding the signal back to the inverting terminal. Okay. And what's 1 LSB? It's 10 volts over so it's 10 volts over 16. No, 32, 5-bit. Sorry. Is that correct? Over 32? Mm-hmm. So what is one ISB? Yeah, so we can calculate for that one ISB, right? And then start with 5-bit. Keep in mind, 5-bit. You need 6 states to get the conversion done. So 5 bits, but you immediately know that this is a half of the overall voltage. This is 5 volts. So I'm going to start with this one and compare with. So here's the 5 volts. Compare with 6.2 is reporting a 1. So that one is being inserted where? Here. So whatever voltage it is, but now it's giving you 1, 1, 0, 0, 0. How to calculate the voltage of this one, of this number? It is 11000 times 10 volts over 32, right? That's one LSB. This is how many LSBs it has. So you can calculate the voltage here. So you can use your smartphone if you don't have a calculator with you, right? I won't say you're cheating. I trust everyone. So just directly grab whatever calculator you have. And then, you know, this is definitely, okay, 7.5. So 7.5 here, so you're getting a 0. So 0 is being inserted here. 1, oh, sorry, should be at the bottom. 1, 0, 1, 0, 0. That voltage is 6.25. 6.25 is still larger than this guy, but still reporting a 0. And now it is 1, 0, 0, 1, 0, right? And that one is 5.625, which is smaller than this number. So it's going to report a 1, and it becomes 1, 1, 0. Is that correct? Oh, no, no, no. Oh, yeah, yeah. 1, 0, 0, 1, 1. And that is 5.9. And this is going to report 0. And the result will be 1. Oh, be a 1. Yeah, that's right. And done. That's it, right? Okay. Any questions? No? These two, I'm going to do it really quick because I don't want to spend all the class. The first one, there are some problems for the with the simplification. So if you look at AB something or AB, it's going to be AB. So this one is AB or CDE. Any question on that? So it becomes becomes this. AB in parallel. And then CDE. Does that work? This must be A. This must be B. No other options. You cannot say BA. It's going to be wrong. Won't pass LVS, or so it's called LVS in cadence and it's called NCC in electric VLSI. So LVS makes more sense. It's layout versus schematic. It's comparing schematic and layout, checking if they match. So I have to have A here, B here, because A is on the top. C, D, E, no other options, but you have options here. But it's better to have A here, B here, C, D, E, like this. For the second one, you cannot simplify that too much, right? So just give up, don't simplify, don't spend like 10 minutes to simplify it. How can I tell usually? Sometimes you don't know if you want to simplify, sometimes it cannot be simplified, but spend too much time on it. How can I avoid that problem in the future? So here's how you can make a conclusion. It's so important to make conclusions for everything. Like I think when you compare why other people can do a better job, it's just because they make more conclusions every day. So now here's the point, you want to make a conclusion. What is that? Or how can you avoid that problem in the future? So expand this one first. So DEEF, so electrical engineering, it's just DEF, right? So E and E is still E. Can I simplify this further? No, right? Cannot simplify this anymore. And you have three minterms. Remember minterms in logic? It's just several components are being ANDed. It doesn't matter for the name, but just look at this form. It's A, B, C, D, F, D, A. If you combine these two, which is fine, but I think it's making things more complicated. Right? If you just directly use this one, it's actually easier. DF. This is more straightforward. So this is actually pretty easy. It's not difficult since we know how to form a 3 parallel transistor. So what if we just do this? So here's a top rail. Sorry for that. Ignore the black line in the middle. What about this? If I connect this one to here, then I got 2 and 2, then merge into 1, and it's gonna work, right? Is that correct? Any questions on this? For the last one, I didn't even change the number on it. Okay. Ideal output. You have to list all the ideal ones. And when you are calculating DNLs, you are calculating the steps compared with one LSB. So just check out the solution I have. I wrote down all the details about the same problem during one of the lectures you can refer to on my website, right? So there's a note, PDF notes, so you can look at it. All right, any other questions on the midterm? No? No worries, I made the same mistakes when I was in college, when I was a student. So fail on one single problem for many times. Happened to me as well. Don't get frustrated. Happens. How can I avoid it next time, right? Just have some conclusions here right now. Not happening in the future. So let's look at some of the examples for BJTs. So we are done for BJTs, and you can start working on the homework problems. Start with this one. It's called VPP. So VCC. That's a circuit. So the first question is, determine the Q point and find the maximum peak value of the base current. So whenever this circuit has been biased like this, it's already being operated at a quiescent point. So there's a Q point already happening. Can be the best option, can be a bad option, but whatever. Right here's a load line. It's already operated somewhere. You agree with that? It's already properly biased. So the current, all the DC current is running through the transistor. Already set up the DC offset and everything, the current values, everything is known right now. No variables, everything is known. You can solve for every single current in this circuit whenever it's being biased by this. You got a base voltage, DC voltage, you have a collector voltage. It's operating right now. It's the Q point. Q point is defined by VIC and VCE. Because remember, for this curve, the x-axis is VCE, and the y-axis is IC. Since you have this DC is being operated by all the DC sources, and there's no AC value, so the change of the voltage from B to E is tiny. So you can directly assume that the DC voltage here is 0.7 volts. And after that, I can calculate for IB. So IB right now is also IBQ because it's already being operated at the Q point. So IC, VC are known, IB is given as well because IC is already, you can calculate for IC for this value. And beta is 100, I think for this case. Beta is 200. So you can directly calculate for IB, which is called IBQ because it's IB at Q point. So IBQ is VBB minus VBE, the DC voltage of the VB is 0.7 volts, and divided by RB, right? Which is 10 volts minus 0.7 volts over 47 kilo ohms. So that is 198 microamps. So once IB is calculated, you can calculate for IC easily because IC equals to IBQ times beta, which is 198 microamps times 200. This gives you 39.6 milliamps. So VCE, what is VC? It's very simple. It's VCC minus the voltage drop across the resistor. So VCE is VCC minus IC times RC, which is 20 volts minus IC is here, 39.6 milliamps, times RC, which is 330 ohms. So I'm getting 6.93 volts. So the Q point has been calculated. I know the Q point, just keep in mind, Q point is being defined by IC and VCE, right? If you know IC, know VCE, which is actually, you know X and Y in this coordinate, you know that where the point is, right? So you know the Q point. So you want to just calculate for VC and IC in order to get a Q point. If it's asking you to get a Q point, so the bottom line is get ICQ and VCQ. You're done with the Q point. So what about second question? Determine the Q point, done, and find the peak value of the base current. So if this one is being biased at this point on the curve, then you know that this is maximum. And if the sine wave is only able to swing like this, but not this. So the maximum swing will be here. Does that make sense? If you don't have enough room, you want to make it symmetric. All right, so that's the bottom line. And now it's being biased over here. So the problem is you cannot swing the same range here as you can swing here. So this will be the maximum signal swing as the output. If you convert it into IC, same thing. You cannot swing the signal to the largest IC because of the Q point is not being set up at the correct value, or the correct, you're not using the correct Q point. It's not an ideal case. So now we know the Q point. How can you find the maximum swing in this case? Let's don't talk about, because this is asking you to find the peak value of the base current. You know, but we don't have the base current here being plotted in this curve. We don't have IC. So we just need to find out the maximum peak value of IC, and we divide it by beta, we can get the peak value of IB, which is the input. So we're going to tell the user that the input cannot be larger than that number, so you are not saturating the output. Okay? So now we know the Q point is over here. It's not in the middle of the IC. So what's the maximum value? How do you know that? How do you know what's the, so right now we just want to calculate for this one. So how do we know that? How to calculate it? Do we know if the Q point is over here or over here? We don't know yet. How can I find out? Compare. So now we have the IC. We know it's being operated over here. I just plot it over here, but I don't know. This guy probably is here, right? Gotta compare this with which. There are two ways to do it. First, you can compare this current, which is some point on the y-axis, and compare that value with a half of the IC. So you'll know it's above that half or below that half IC. Second, you can just use, so this value is definitely from that point to 0. And you know the largest IC, so you can calculate like which one has a larger room, and you want to use the smaller one as a range. Does that make sense? Does that make sense there? Everyone? I don't want to miss anyone, losing anyone. So we know that, and now we don't know Icsat. So this largest IC is called Icsat. So now let's calculate for Icsat. So what is Icsat? So for this one, how to calculate the largest IC can possibly flow in the channel. So whenever IC is the largest, from the curve, from the load line, you can tell that VC is 0. So when VC is 0, it's literally just the VCC over this load resistor. Because VCE is 0 at that point. So it's going to be VCC over RC. Which is 20 volts over 330 ohms. So that one is 30.6 milliamps. So here's 60.6 milliamps. So that's the largest IC. And now it's being biased here. So is this on the upper half or lower half. This IC, upper half, right? So which range you want to use? The smaller range, right? A smaller range. What is a smaller range? It's going to be Icsat minus ICQ, which is 60.6 milliamps minus 39.6 milliamps, which is 21 milliamps will be the range for the IC to swing. Because right now it's over here, IC is being actually being biased, not here, it's here. So you don't have much room to swing on the top. That's the only range you can swing the signal as the output, which is IC, right? So here is the largest swing. And you can calculate IB from that. So that gap here is 21 milliamps. Okay, it's already calculated. So it's actually both, right? It's the full range here, peak to peak. Which is wrong, not peak to peak, just from the middle. Just a peak. So you guys are bumped. Whatever I'm saying, you are just accepting. Or you want to give me a signal like received. Like whenever you send somebody an email, they'll just reply you one word, received. Can I request this is received? I know you're bumped, right, by the midterm exam. Is that the peak to peak or just half? Half, right? The Q point set up the swing, the middle line to swing the signal. So I'm using the so that's a middle line here, and that's the largest. So that's half of the signal. So that's a peak voltage, the current for IC. So for IB, so the maximum swing range for IB (21 milliamps over beta, which is 21 milliamps over 200. What is that? 105 microamps. It's done for this problem. All right, next. I ask you, for example, if there's a circuit looks like this, and that is VCC. If there's a circuit looks like this, it's actually being self-biased. The reason it's being biased is because it's using that VCC, which is DC voltage, to supply a IB here. So it's already being operated at a certain Q point. You can calculate for the Q point. Use a similar way like we just did over here. And also, at the same time, if I'm asking you to draw the load line, draw the load line, can you draw it? For example, all the resistance are given, and VCC is given as well, the beta is given. So can you draw the load line? It's very simple. How do you draw the load line? Are doing the homework assignment. So after this class, you're going to do the homework assignment, right? So how can we draw the load line? Find VCE, find IC, just draw it. And you have to draw the Q point on the load line. So what's the Q? Where's the Q point? It's already being biased properly. So it's being operated at a certain Q point. So whenever the Q point can be in the middle, can be here, can be here. Whenever you are drawing that Q point, for example, is over here, you want to show the X and Y values, right? So what's this ICQ? What's this VCEQ? You want to show that on the load line. So that's a complete load line or Q point drawing you want to turn in, right? Which is totally doable. And the bottom line is, if this Q point is at the upper half of the range, you want to draw it at the lower half. I can definitely tell it's wrong, right? If it's in the middle, usually it won't happen. You want to just draw it in the middle. If it's over here, you want to estimate that a little bit. Okay. That's one problem you'll see in the homework 7, I guess. Still next Monday. And so expect a little quiz on Monday. Can be very similar problems, to whatever you are seeing in homework 7. So let's talk about the last one here first before we quit today. This is kind of different. So this is amplifier. And that's a voltage divider. So this is a voltage divider. So this provides a DC bias to this thing. If you consider, it's very useful for understanding what is a superposition, right? So this capacitor is going to remove any DC component here. So this is a high pass filter. Because DC cannot pass that cap, but AC can pass. So AC signal is passing, which is a signal you want to amplify. It's going to pass this DC as this cap. The reason we want to do that, we want to use a high pass filter to filter out the DC offset is because in the environment, whenever you collect a signal from the sensor, there might be a DC component in there, and you want to use it. And you have to use a certain DC offset to lift that signal swing to a certain DC level. And the way to do that is you have to remove any of the DC component from the sensor first. The analog input has a DC over there. You want to remove it because the DC can change, depends on different settings. So remove that important, very, very practical. I mean, you probably will take analog, you will take circuit tool, you will take all the other electrical engineering courses from any institutions, from any professors, but they'll never tell this to you guys, okay? It's very practical. You get a sensor, it's sending analog signal to amplifier. It has a little DC offset, and that DC offset may change, depends on temperature, depends on all the other settings, and that's not a signal. It doesn't carry information, it's just a DC line. So you have your AC signal swing around that DC line, which changes. It's horrible. You want to remove it. How to remove it? Get a high pass filter. So this little front end high pass filter is going to remove everything from this signal source and just provide a pure AC swing. But the thing is, your amplifier really requires a certain DC offset for any signal it's receiving. It's going to set up that DC. For example, you have a reel-to-reel. You want to set up the DC in the middle because you will get the largest swing on both sides, but not the DC offset from the sensor. Sometimes can be here, it can be random. Can be here. Just want to remove it. Remove it first, and then do a superposition. Can you tell this is superposition? Why superposition? If you don't look at anything else here, it's an AC signal, it's just added to this point, right? It's AC voltage being added to it. And now you short everything here. Just look at this DC signal, which is the VCC being divided by these two resistors. It's a voltage divider, so it's adding a DC voltage to it. So it's actually literally like a something swing around anything, right? You remove that thing, and so bring it to the baseline, and then lift it to a desired DC offset. That's the whole point. It's being used everywhere with operational amplifiers. Critical. So you lift it. How you lift it? Superposition. You just add a DC to it. It's going to lift the signal. All right, and then, because this one has been biased at a certain DC point, it's going to amplify it through IB. So that voltage is being converted into a IB, and IB is being amplified by beta times to here. So times the load line is being converted to a voltage amplification, so voltage output from here. All right, so the signal, whatever signal it is going to be, and VCC is 12 volts, and this VRE is 1 volt. So if this is given, can you calculate all the resistance in order to design this circuit amplifier? So in real life, in the real world applications, the signals are any type of analog signal you want to amplify it using a BJT amplifier, for example. It's not only way you can amplify the signal, definitely not the best way. If you want to make it simple, you just want to make a little amplifier with a BJT transistor, right? You want to design this resistance. You don't know what are these yet. So you're designing the circuit, okay? But you know what this voltage is. For example, you want to set up a little room from the ground. You want to lift this voltage a little bit so it's not shorting anything. If this is, it's not shorting this signal to the ground. So in that case, this is given. For example, it's 1 volt. I just want to constantly provide a DC voltage over here, and that's given. So now it's asking you to design the circuit. Design the circuit means you want to design the resistance values, right? This is what you can grab from the drawers and plug into the circuit and build out the circuit. You know the transistor you want to use already. It's right there. Beta equals to 100, 200, doesn't matter, right? You know that that's the only transistor we have. So there are some considerations whenever you're designing this amplifier. And we'll take probably 10 minutes on Wednesday to cover this. You'll see this problem on the homework assignment. You're not ready to do it yet, but we'll take 10 minutes to cover it on Wednesday. And you'll be ready to do the homework. It's due next Monday. Okay? See you on Wednesday or Tuesday.